A very good morning to one and all. Myself, Vamshi. Today I am discussing about a topic of complex numbers and phasors without vectors or one. Coming to introduction part of the complex numbers and phasors. Complex numbers are numbers that can be expressed in the form of a plus bi, where a and b are real numbers and I is the imaginary. In complex number, it is nothing but a formula expressed as a plus bi. A is nothing. A and b are the nothing but the alphabets. These are real numbers and I is the imaginary unit. Phasors are complex numbers that represent sinusoidal functions in frequency obtained. Phasors and complex numbers that will represent sinusoidal functions that represent the sinusoidal functions in the frequency domain. Understanding the complex numbers and phasors is essential in analysis of electrical circuits and signals. It is very mandatory to understand the phasors and the complex numbers in electrical circuits and signals. It will be very useful further. Representation of complex numbers. The real part of a complex number is represented on the horizontal axis while the imaginary part is represented on the vertical axis. There will be horizontal axis and the vertical axis, two axes is there. In this horizontal axis, the real part of complex number is represented on horizontal axis and imaginary part is represented on a vertical axis. Complex numbers can also be represented in polar form r less than theta, where r is the magnitude and theta is the phase angle. Complex numbers will be represented on a polar form such as r is equal to theta, where r is the magnitude and theta is also known as a phase angle. The magnitude of complex numbers is given by z equal to square root of a square plus b square. Arithmetic operation with complex numbers. Addition and subtraction of complex numbers involve adding or subtracting the real and imaginary parts separately. In this complex number, there will be the addition and subtraction by between adding the numbers and subtracting, deleting the numbers of real and imaginary, which will be done on separately parts. Multiplication of numbers involves expanding in the terms and simplifying using the properties of I square equal to minus 1. And it's also addition, subtraction and the multiplication also will be done on a complex number, which is the property of I square equal to minus 1. And in this division also done. Division of complex numbers is done by multiplying both the numerator and the denominator by conjugated denominator, and will be multiplied by, in the division will be multiplied by the both the numerator and the denominator. Euler's formula. Euler's formula relates complex numbers to trigonometric function e I theta equal to cos theta plus I. It is the formula for the Euler's formula and sin theta. Euler's formula, it is a fundamental is understanding the relationship between the complex numbers and phasors. It is the fundamental formula which is easy to understand the relationship between the complex numbers and the phasors. Phasors representation, which is will be done on a mini of circle. It is the shape. Phasors are used to represent the sinusoidal signals in the frequency domain. It is phasors are mainly used to represent the sinusoidal signals of frequency domain. A phasor is a complex number whose magnitude represents the amplitude of the sinusoidal signal and angle represents the phase shift. Phasors simplify the analysis of sinusoidal signals in circuits and systems. Phasor addition and subtraction. Adding or subtracting phasors involve vector addition or subtracting into the complex plane. The magnitude of the resultant phasor is given by the Pythagorean theorem. The magnitude of the phasor, further we can use the theorem that is known as the Pythagorean theorem. The angle for the resultant phasor is determined by the inverse tangent function. Phasor multiplication and division. Multiplying phasors involves multiplying and the magnitudes and adding the angles. Dividing phasors requires dividing the magnitudes and subtracting the angles. Phasor multiplication and division simplify the analysis. Phasor multiplication and division simplify the analysis of complex impedance in AC circuits. And the multiplying phasors, in these multiplying phasors, it involves the multiplying the magnitude and adding the angles. And then coming to dividing phasors, it requires a dividing the magnitude and subtracting the angle. In this multiplication division, will be difference will be there. Phasor multiplication and division simplify the analysis of complex impedance in AC circuits. It is AC circuits complex impedance can be easily solved. Phasor diagram. A phasor diagram is a graphical representation of phasors in complex plane. It is a graphical representation of phasors which will be done in complex plane. Phasors are represented as arrows with a specific magnitude and angle. Phasors are represented as arrows with specific magnitude and angle. Phasor diagrams help visualize the relationship between differential phasors in a circuit. Phasor applications in AC circuits. Phasors are used to analyze AC circuit with resistors, capacitors and inductors. Phasors are used to analyze AC circuits with resistors, capacitors and inductors. Impedance in AC circuit is represented as a phasor that incorporates both magnitude and phase angle. Phasor analysis simplifies calculations and circuit analysis in the frequency domain. Phasor analysis simplifies calculations and circuit analysis in frequency domain. Phasor analysis power systems. Coming to power systems, phasors are utilized in power systems for analyzing voltage, current and power relationship. Power factor correction in power systems can be achieved through phasor analysis. Power factor correction will be done in power system with the phasor analysis only. Phasor analysis helps to optimize power flow and improve system efficiency. Phasor transformations. Phasor transformations involve converting between different frames or coordinate systems. Transformation of phasors is essential in power system stability, analysis and control. Phasor transformation facilitate the analysis of complex power systems. Application of complex numbers is signal processing. Complex numbers are used in signal processing for analyzing and manipulating signals. Fourier transformation and Laplace transforms involve complex numbers in representing signals. Complex numbers plays a crucial role in digital signal processing algorithms. Complex numbers in quantum mechanics are complex numbers which are also used in quantum mechanics. These are fundamental in quantum mechanics for representing wave functions and the probabilities. Mechanics for representing wave functions and the probabilities. Quantum states are described by complex numbers known as probability amplitude. Quantum states are, in these complex numbers are also known as probability amplitudes. The Schrödinger equation involves complex numbers to model the behavior of quantum systems. Complex numbers in control system. Complex numbers are used in control systems for analyzing stability and response of systems. It is used in analyzing stability and response. Transfer functions in control systems involve complex numbers to represent system dynamics. Root locus and Nicholas plots are graphical representations that utilize complex numbers. Limitations and challenges with complex numbers are complex numbers can introduce additional complexity in mathematical calculation. It will be additionally we can introduce complexity in mathematical calculations. Imaginary numbers may lead in interpretation challenges in certain contexts. Understanding and interpreting complex numbers required a solid foundation in mathematics. Complex numbers can introduce additional complexity in mathematical calculation. Complex number it will be introduce additional complexity in mathematical calculations. Imaginary numbers may lead to interpretation challenges in certain contexts. In this, imaginary numbers may also be gives interpretation challenges in certain contexts. Understanding and interpreting complex numbers require a solid foundation in mathematics. For understanding these complex numbers, this have to be solid foundation in mathematics will be there. Coming to conclusion part. Complex numbers and phasors play a crucial role in various scientific and engineering disciplines. These complex numbers and phasors it is very important and it also plays in very many subjects and it's also the engineering displays like in control system and the power system and mathematical also phasor and the complex numbers will be used hugely and more. The understanding of complex numbers provides a powerful tool for analyzing signals and systems. The understanding of complex numbers provides a powerful tool for analyzing signals and systems. Phasor representation simplifies the analysis of sinusoidal signals and facilitates calculations in the frequency domain.